Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on colorimetric characterization of multispectral imaging systems. Multispectral cameras usually have 4 to 16 or even more spectral bands, and they are used in many fields like agriculture, remote sensing, art conservation, and so on. In this video, I want to show you how you could colorimetrically characterize them. Let's get started. As I said in this video, I want to talk about colorimetric characterization of multispectral imaging systems. Multispectral imaging systems play a crucial role across various fields due to their ability to capture detailed spectral information beyond what is visible to the human eye. Some key applications of multispectral imaging systems include enhanced analysis and discrimination, quality control and inspection, medical diagnostics and imaging, environmental monitoring and management, remote sensing and geospatial applications, and forensic analysis and cultural heritage preservation. Multispectral imaging systems come in various configurations, each tailored to specific applications and requirements. Here are some different types of multispectral imaging systems. The first is filter-based multispectral imaging systems. These systems use a single sensor coupled with a filter wheel or a filter array to sequentially capture images at different wavelengths or spectral bands. Another setup that falls under this category is using a bunch of colored LEDs and a monochrome sensor. The colored LEDs in a sense do the same job as different filters. The second system is prism-based multispectral imaging systems. Prism-based systems use a prism to split incoming light into different spectral bands, which are then directed onto individual sensors or detectors. Each sensor captures a specific spectral band simultaneously, allowing for faster image acquisition compared to filter-based systems. The third one is hyperspectral imaging systems. Hyperspectral imaging systems capture images across hundreds or even thousands of narrow contiguous spectral bands. Snapshot and fiber-coupled multispectral imaging systems are also two different types of multispectral imaging systems that are currently built, and we are not going to cover them here. In this video, I want to talk about the colorimetric characterization of a multispectral imaging system that is assembled using colored LEDs and a monochrome sensor. This camera outputs 16 bands from UV to near IR. It is worth noting that we don't need all these channels for colorimetric color reproduction. We only use the 12 of the channels from 395 nanometer to 730 nanometer that fall within the visible part of the spectrum. The colorimetric characterization in a sense means to transform the camera response to a standard colorimetric value under a specific viewing condition in terms of observer and light source. An example can be going from camera response to 1931 CIEXY stimulus values under D65 standard illuminant. In other words, we would be able to reproduce the true color of the objects imaged by the multispectral imaging system. We have already shown how you can do this using an ordinary RGB digital camera, which you can find in one of my prior videos. But in this video, I want to show you how you can do that using a multispectral imaging system. The process is very similar to that of a digital camera, but the only difference is we are dealing with 12 channels, not 3. In general, it is expected that a multispectral imaging system would lead to a much more accurate true color reproduction as opposed to an RGB camera, as the multispectral imaging system outputs more channels, hence providing more amount of information about the spectral characteristics of the objects imaged. This in turn leads to a less erroneous colorimetric color reproduction of the object. In the case of the RGB camera, on the other hand, the camera outputs only 3 channels, limiting the amount of data provided, resulting in an erroneous true color reproduction. The colorimetric characterization of the multispectral imaging system, like this one in this video, ensures accurate color reproduction in captured images. This is particularly important in applications where color fidelity is critical, such as in medical imaging or color grading for film and photography. 2 steps are used to colorimetrically characterize the multispectral imaging systems. First is linearizing the camera photometric response using the neutral samples of the Macbeth color checker or any other color chart you have. Second is developing the transformation matrix from the linearized camera response to CIEXY stimulus values using the mean patch values of the color chart. Linearizing the camera photometric response ensures that the camera response is linearly related to the Y stimulus value. In order to do that, the transfer function is fitted between the luminance factor and normalized digital counts. The luminance factor is defined as y over yn, where y and yn represent the white raw stimulus values of the Macbeth color checker neutral samples and the perfect reflecting diffuser respectively. For example, the multispectral imaging system under study here is a 16-bit per channel system. Linearizing the camera response can be written as this equation, where LCRI denotes the linearized camera response for the ith channel, DI represents the digital counts of the ith channel, and 65535 is the maximum digital count for a 16-bit per channel system. The linearized camera response is a linear function of the normalized digital count, here written as f. One should note that this linearization is performed for each spectral band or channel, and every channel will have its own specific transfer function. Now that we have linearized the camera photometric response, we are able to linearly transform it to the CIE-XYZ tristimulus values. In order to do that, a 3x12 matrix is derived relating the camera response to the CIE-XYZ tristimulus values. Here we use the mean patch values of the Macbeth color checker when it is imaged with the camera. For example, the multispectral camera under study has 12 channels in the visible part of the spectrum, and the color chart has 12 patches. Therefore, the matrix LCR holding the mean patch values of the color chart is of size 12 by 24. We also know the CIE-XYZ tristimulus values of the color chart, which are saved in the XYZ matrix of size 3 by 24. For the colorimetric characterization, we need to find the matrix M that transfers the camera response to CIE-XYZ tristimulus values, as written here, where M is the transformation matrix relating the camera response to the CIE-XYZ tristimulus values. LCR represents the linearized camera response, and XYZ denotes the CIE-XYZ tristimulus values of the 1931 standard observer under D65 standard illuminant. Now we use the known CIE-XYZ tristimulus values of the color chart to determine the matrix M as shown here, where this here indicates the pseudo inverse of the matrix containing the linearized camera response. Now that the matrix M is estimated, we can use it to transfer any image taken by the camera into CIE-XYZ tristimulus values. The tristimulus values are then converted into sRGB values using standard formulas for the purpose of visualization. It is also very important to know that we also performed flat fielding, which is a technique used in digital imaging to correct for irregularities and variations in sensitivity across the detector or in the optical system itself. These irregularities can result in uneven brightness or color in the final image. The process involves capturing an image of a uniform white surface. Therefore, in this video, we have images of the object in 12 channels along with images of the white surface in 12 channels. Let's go to MATLAB and show you a practical example. First and foremost, let me show you guys the data that I have. These are the raw images of the color chart from 395 to 730 nanometer, as I said before. And these are the images of the white surface for the purpose of the flat fielding. And these are the images of an object other than the color chart. Okay, let's start with the colorimetric characterization. These are some of the programs you need to run to colorimetrically characterize your multispectral imaging system. I'm going to put all these in my GitHub, and you could access them through a link in the description section of my video. The first program we need is color checker bands. This one is going to perform flat fielding and also turn the camera response into a meaningful spectral reflectance value for the color checker. We first reading the color checker, and then we're reading the images of the white surface, and also we have to specify where we want to save the results. My color checker has 24 patches, in other words, it has 4 rows and 6 columns. So you have to specify that here. And then this function here, which specifies where each patch is located on our Macbeth color checker. And then here you have to specify where your white patch is located, which is going to be 19 for Macbeth color checker. And then here is where we perform flat fielding and also turn the camera response into a meaningful spectral reflectance value. And then we're going to be saving all the bands one by one. Let's run this one and obtain the flat fielded bands of the Macbeth color checker. You have to first run it, specify where the color chart is located, which is here. And then it's asking for the flat field image, which is the white surface. And then it's asking for the result folder, and I'm going to save them just here. Now you have to mark 4 corners on the Macbeth color checker. The first one is here, the second one is here, the third one is near the white patch, and the fourth one is near the black patch. Now these are the 12 bands of the MakePath color checker that we just flat filled. Now that we have the flat filled bands of MakePath color checker, we should calculate the mean patch values of it, which is going to be done using this program, color checker mean values. First we have to read in the flat filled image, and then the size of our color checker is 4x6, and then the same function as before, which is going to locate the patches of the MakePath color checker. And then we're going to calculate the mean patch value and the standard deviations here. And we're going to save the results. Let's run it. Now we have to select the folder that contains the flat filled image, which is going to be here. Again, the same thing. The first point, second, the third point is near the white patch. The fourth point is near the black patch. As you can see, it's saving the mean patch value and also the standard deviation for each patch. So when the calculation is done, it's going to ask me where you want the results to be saved, and I'm going to save it just here. And you can see this is the mean patch value, and this is the standard deviation for each patch. Having the mean patch value and the standard deviation is going to enable us to calculate the SNR. In case you were interested, all you have to do is to just divide the mean patch value by the standard deviation for each patch, and then you're going to obtain the SNR for each patch. And if you needed an overall SNR, all you have to do is to just average those SNRs for each patch. Okay, now that we have the mean patch value, we could perform the colorimetric characterization. We need this one. But we still haven't done one thing. We have to linearize the camera response. This equation is a linearized camera response. But how we obtain this, we use Excel. Let me show you guys. I've already performed this. So for each channel, you have to linearize the camera response, and I just fed a linear equation to each. The first column is the camera response for the neutral patches, from white to black. And then the second column is the normalized white tri-stimulus value of the same patches. So let me show you guys. Let me clean this one. You already have to have the CIE XYZ tri-stimulus values of the MakePath color checker. For me, it's XYZ value that I have here. And we already calculated the mean patch value of the MakePath color checker, which is here. So this one and this one. So the left column is the camera response for the neutral samples, which is here. So the camera response for the neutral patches is here for the first channel. So these guys go here. And then the second column is the normalized white tri-stimulus values of the neutral patches, which is here. White tri-stimulus values of the neutral patches. So this second column is the same in all of them. But the first column is the camera response for that channel to the neutral patches. And I just showed you how you could obtain them. And then very easily you just fit a linear model. I use linear model because that keeps the noise very low. And as you can see, the R square is not bad. So the linear model, as long as the R square is about 0.9, is fine. And you don't need to have a fancy nonlinear model. You could see that here R square is 0.88, but I'm going to use linear model because otherwise the noise is going to be accentuated in my images. So to keep the noise as low as possible, it's better to just use a linear model. Okay, let me show you guys how you could do it for this one. Let me first delete this one. So I just deleted the whole thing. All I have to do is just first choose these points, inserts, charts, this one, and then come down here. I'm gonna just put it here, and then right click, add trend line, and I'm gonna just choose linear as I said, and then I'm going to choose this option so that I know what the equation is, and also show the R square. So it's very easy with Excel, and that's why I use it. Now that we have linearized the camera response, we go back. First I'm going to load the mean patch values, then I'm going to linearize them using the equations that I just specified, and then I know the CIE XYZ tri-stimulus values of my MakePath color checker. And then this is where I'm specifying matrix M, the matrix that helps me colorimetrically characterize my camera. And then I'm going to start reading the bands one by one. I'm going to reshape them into a matrix form. And then I'm going to linearize each band using the equations that I just specified. And then I'm going to change the image into XYZ and then into sRGB using this function. Let me open this function quickly. This function uses standard color science formula to change the XYZ into sRGB, and I'm going to include it in my GitHub as well. And then this is where I'm contrast stretching the image, and then this is where I'm clipping the image so that the values under 0 and over 1 are going to be clipped. And then I'm going to change the image into UINT16, and then I'm reshaping it into an image, and then I'm going to show it and then save it. Let me run this one and show you guys the result. So this is the result of the colorimetric characterization, and an image has also been saved here, which is this one. Very easily. Now let's go and apply it to a new image. Again, first you have to flat fill the image. To do that, I'm going to use this program, other objects. This is going to do the same thing as before. First we're going to specify where the color chart is located, and then the image of the white surface, and then the image of the object. But everything else is the same as before. And this is where the flat filling is performed and the camera response is turned into a spectral reflectance value. Now let's run this program. You have to first specify where the target is again, which is here, and then the flat filled image, which is here. These are all raw images. And now the new image, which is here. Where I want the images to be saved, I want them to be here. Now again, the same thing as before. First point, second point, third point is near the white, fourth point is near the black. And now this is going to perform the flat filling on my new image. Let's go to the folder. These are the 12 bands captured of my new object. Now I want to obtain the colorimetrically characterized image of this object. I'm going to run this program. So again, I'm going to put all the programs in this video on my GitHub, and you could access them using the link in the description section of my video. This is the program that we have to run. And as you can see, this is very easy. We just have to read the images, and then we linearize each band using the equations that I already spoke about. And then this is the matrix M, which I have saved as M12 because it's for 12 channels. And the matrix M is very important, as I said, because this is the matrix that colorimetrically characterizes your system. So I just have to use the matrix M to obtain the CIEXYZ image of these bands. And then I'm going to change them into sRGB. And I'm going to contrast stretch them. And then I'm going to clip the values under 0 and over 1. And then I'm going to change that into UINT16. And I'm going to reshape it as an image. And I'm going to show it to you guys, and I'm going to save it here. I'll also combine the short, middle, and long wavelengths to show you guys the result as opposed to a colorimetrically characterized image. Let's run this. So this is the result of the colorimetric characterization, and this is the result when I have combined short, middle, and long wavelengths. And the images are going to be also saved here. The colorimetric characterization, this is the band combination. They're not the same at all. But this image is much more accurate than this one because this is colorimetrically characterized. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.